All right, hi everyone. My name is Sage. Today I'm going to be walking you through the post-lab calculations for our second experiment, colligative properties. And there's a lot going on here, but we'll break it down step by step, and it should hopefully make it a bit easier for you guys to understand and to appreciate what we're doing here, because it's pretty cool. If you don't have Excel already, you can download it through your UC Merced email for free. Just go to office365.com, I think, and log in there and just download it. And you guys will have free access and can follow along with what I'm doing here. Now, so I'll be going over some Excel tips as well if you don't know them. This one's a pretty easy one. Just start, first pause this video and make this kind of template for yourself. Here I have time and I have temperature. Just start with that. It'll be fine. So at time 0, let's say we started at 20 degrees Celsius. Now, a quick tip to fill out the rest of this time chart, you can do equals. That's how we start a formula in Excel. And you can click on the space above it and add 20 because we're taking measurements every 20 seconds. And then just click on the cell, drag at the bottom right, and boom, that's all filled out. Quick and easy. All right, so we're going to now decrease our temperature according to the data you received in your first, I think it was part 2 for your dichlorobenzene measurements. Just plug in your data here for all of your time measurements. Okay. So what I'm going to do here, I'm going to paste in some sample data. Don't use it. It'll give you incorrect results and will be obvious that you used fake data because we also have your pre-labs. So don't do that. Yeah, just pasting that in. And you can see here, this is a good cooling curve data set. So we can just make a graph very easily by selecting this set of data. We can insert and then do a scatter plot up here. Oh, yeah, see, weird data. We don't want to use it. Okay. The first thing I want you to notice here in our pre-lab lecture, I pointed out what kind of lines we're going to be using to calculate our freezing temperature for this cooling curve. In reality, our temperature is going to be somewhere over here, some point that we never explicitly measured during our experimentation. And that's for reasons we won't go into. But how we are going to fix that is we are going to use the intersection between our initial decrease in temperature here between these first 2 points and that line's intersection with this linear portion of our graph over here. So it's going to meet somewhere over here, and you'll see what that means as I do this. So first, let's make a line here. I'm going to right click on this chart. I'm going to select data. And then you see this thing over here. Let's see, we're going to add another series here, series 2. And then we need to specify the chart range for this. How we're going to do that, we are going to press this button. It'll let us select our X values, and our X values, remember, are for time. So we want to first be doing our first 2 points. So we're just going to do these first 2 points, get our X data there, and get our Y data here. And then boom, we have a new series. A series is what we call just a set of data being displayed in an Excel graph. Okay, and we can name it. We can name it initial. Sure, gets the job done. Now I'm going to click on our data for initial, right click, and then we can add a trend line. So you see it automatically starts plotting here. What I'm going to do, I'm going to, it's linear, which is what we want. I'll display this equation on chart just so that we can see it. And with that, it would probably be a good idea to color code everything. You can color code it. I'm going to leave it and just leave it by the line that we're interested in. And then, cool, we have our first series. And now let's do it for our second series. It's going to be our last 4 data points. So once again, just make sure you're not having anything selected in the chart. When you're right-clicking, it'll mess things up. Go into select data again, add another series with this little plus sign here. It might be a little different for people on PC or Windows, whatever. It doesn't matter. Yeah, so we'll name this final. Sure, doesn't matter. No one's going to see it anyway. And so we're picking our last 4 data points. So I'm picking the last 4 points for my time. And we can go back here. That's selected. Now we're picking our Y, the last 4 Y points. Cool. And that changed the color over here, you can see. I'm going to once again right-click after I've clicked once on one of these points in our series. And then I can add a trend line. You could also do this, I think, on Windows. There should be an option for like format series, I think, and it'll get you to this. There's a couple different ways of getting to this point. So just mess around with it, see what you have to do. Once again, display equation on chart. Awesome. Okay, so now we have the equations for both series of our data. Now what do we do? Well, we want to find the point where these lines meet, because imagine these lines extending farther out. They're going to meet somewhere over here. At this point, it might be helpful to identify what our M's and B's are in these equations here. If you don't know, the equation for a line can be represented as y is equal to mx plus b. You can see that here y is equal to mx plus b. M is the slope, b is the y-intercept of any given line. Ignore this. Okay, so let's do M1, which will be our initial equation, or equation 1. Our value here will be negative 0.63. M2 will be 0.0015. B1 will be equal to 13. And B2 will be equal to negative 4.28. So from there, they do give you some equations in your procedure document where they, it's basically just y is equal to m1, let me check it, m1 times, in parentheses, b2 minus b1 over m1 minus m2 plus b1. So let's see, we're gonna put that in, I'm just writing this in so you can see it. B2 minus B1 over M1 minus M2. That'll be in parentheses as well. Lots of parentheses going on here that you'll need to be careful for, because otherwise your calculations will be weird. It's there as well. And then it's plus B1, I believe. Let's see. Yeah, plus B1. Okay. So we can now solve for this equation and remember y will be our intercept at this point over here on our graph. So let's just do TF, because we know that this will be the TF for our dichlorobenzene in cyclohexane solution. So we can over here do an equals, because remember that's how we do a formula in Excel, and then we can go M1 times 2 parentheses B2 minus B1, close one of those parentheses, divided by M1. Oh, I need to open another parentheses actually. Open another parentheses, M1 minus M2 plus B1. And that should be complete. Hopefully it doesn't give errors. Cool. Now we found our freezing temperature for dichlorobenzene. And we can just, over here, if you want to fill it in on our table, we could do equals this, just so we have it all in our nice, neat, organized thing up there. Okay, so that was for our first cooling curve. I will get data for the second one. Cool. So this is our new data set. And we can honestly just kind of copy and paste this over, and it'll keep all our formatting, which will be very nice. We could even tidy this up a bit, add chart titles, add labels and stuff like that, all the things that you will probably need. But let's just paste it. And now we can click on this, right click, select data, and now let's adjust our values here. So for series 1, we can do, oh wait, you guys can't see this, can you? You can do chart data range. Oh, we actually can't do that here because our things are weirdly spaced. So let's do X values first. We'll do all the way down to 240 this time because now we have values down to 240. And for our Y values, our new temps over here. Great, okay. Our initial should be the same. It's, oh wait, no, it won't be the same. We need to adjust only the Y values for our temperatures. There we go. That'll show our initial drop. Now we can adjust our final. And let's see, we still need to adjust our Y values here. We also need to adjust our X. So we want the last 4 points, the last 4 stable ones. And be careful if some of you went a bit longer past, make sure you're doing the 4 data points where it starts to level out. And I think we quantified that as a change of no more than 0.4 degrees Celsius. So you can just stop there, wherever that is in your data, but I'm just doing it the last 4 data points here. Let's see, if I do okay, does it change it? Yep, now we're all changed. And you'll see, so we have our equation over here. Is this what it's supposed to be, or is it? Yeah, seems fine. Weird. Okay. So we have our 2 equations here. We can repeat this process for our unknown, because this is our unknown data. You can see here at the top, labeled it unknown. Let's see. So in this case, I'm not going to rewrite those equations. You can if you want. It might help you keep track, but it's up to you. So our M1 will be negative 0.935. Our M2 will be negative 4.55. Our B1 is 26.1, and our B2 is just 0. Cool. And this should have automatically adjusted as well. That's one of the advantages of copying and pasting blocks from before. And it's giving us a weird data. So something's wrong. Hold on, I'll figure it out. Okay, figured it out. I don't know why. It didn't like that last data point. So I just shifted it back one using these, I guess, 5th to second to last data points. And it likes that, I guess. And so we're going with that. And we're just going to edit these M2 values and wait, hold on. We're editing these M2 values. So now we have negative 0.0005, and our B2 value is negative 4.48. There. Now we have something that works. Okay. So we're gonna deposit this up here. This will be the freezing temperature for our unknown, which I'm going to change here. Not our unknown, but the solution that contains our unknown. Just a way of keeping track of what's what. Okay, now let's bring in some masses. Let's say that for the dichlorobenzene, I measured, your range should be somewhere from 0.25 to 0.3. Let's say that I measured 0.26. Cool. Let's say that I measured 0.275 of my unknown. And let's say that the mass of my cyclohexane, when I did the run with the dichlorobenzene, let's say that mass was 3.5 grams. And let's say for the run with my cyclohexane and unknown, let's say that was 3.8. Cool. It'll be a bit different for you guys, but just use what you have. Now, let's fill in the rest of this table. We can start with molality. Okay. I would like to suggest, to make your life a bit easier, maybe converting to moles separately over here. So we're going to do our moles of solutes. And here we can do DC benzene. Maybe make yours not as cramped as mine is. And, oh, you only need it for dichlorobenzene. But anyway, so for dichlorobenzene, our moles is going to be equal to the mass we weighed divided by the molar mass. Because if you think about it, we have a mass in grams, and then our grams need to go on the bottom over here to cancel out and give us moles. That's just how molar masses work. Make sure you know what molar masses are. They are very important. So we're dividing by our molar mass, and that'll give us the moles of our solutes. And if you remember, molality is moles of solute over kilograms of solvent. And our solvent is cyclohexane. We have it in grams, so we for our calculation, we'll need it in kilograms. But anyway, so we need moles of solute, which we have over here, divided by, and then I'm going to do parentheses, grams of cyclohexane, and we want that in kilograms. Remember, 1,000 grams is 1 kilogram, and using unit dimensional analysis in your head or on paper, whatever you need to do to see why I'm doing this, we're dividing by 1,000 grams, so that cancels out and leaves us in kilograms. And that will be our molality. And then molality, we're not calculating that yet for our unknown, because that is what we're interested in. We don't know its molar mass, therefore we can't get to molality, because remember, our molar mass was required in order to get moles of solutes. So that's why we're saving that for last. What we can do, we can first, let's see. Oh yeah, why don't we do this? So delta TF for both of these, it will be equal to, you can see over here, the freezing temperature of our solvent minus the freezing temperature of our solution. The freezing temperature of just our solvent was measured in part 1. I didn't put that here. Okay, let's say that we measured, we have, we'll just say it was 7. Great. So this will be equal to 7 minus our calculated freezing point for our solution. That will give us a TF. We don't know this KF value, this proportionality constant is what that's called. We don't know this. It has to be experimentally calculated, and once we do that, we can then use it to calculate molality, as long as we know the change in freezing temperature. So let's do our solving for KF for our dichlorobenzene, because we do know that. We have everything we need to solve for it. We have our delta TF, and we have our molality. So in your mind, if you wanted to arrange delta TF is equal to KF times molality, you could just divide by molality. And we'll do delta TF divided by molality. And we got a KF of 22.23. Okay, so we switched something around here. Long story short, I'm not going to go into the details of why, but for comparison-wise, we need to switch something around here. Rather than doing F7 minus H2, or in other words, our solvent freezing temperature minus our solution freezing temperature, we're switching that formula around, and we're doing our solution freezing temperature minus the measured. Okay, that'll be our delta TF, it'll be negative. Okay, and so now our KF looks normal, and we can compare it to our actual KF or our theoretical KF value. We'll do that later in these error analysis things over here. Now, what we can do, we can then use this newly found KF value. I'm going to bring up these formulas again because it'll work for this part. We have a, oh, we don't have a delta TF value, do we? Let's fix that. We can calculate this delta TF once again by going equals, remember, we're switching around our formula from what we were doing at first, and we're subtracting the measured value. That'll give us delta TF for our unknown. And now we can use that in this equation. We have delta TF and we know KF. Therefore, we can calculate the molality of the unknown solution. So let's do that. If we want to solve for molality, just do that in your head and you'll be able to see that. I hope you guys can see this, by the way. Yeah, you should be able to, I think. Yeah. Okay. Yeah, so molality. We can solve for molality by dividing out the KF. So let's just do that. Molality will be equal to the delta TF for this solution divided by our KF value for cyclohexane. There we go. Now we have its molality. Now we can do some work on it to calculate the moles and therefore the molar mass of our unknown. So this is relatively easy. For the moles of our unknown, we know that molality is moles of solute, in this case, our unknown, over the kilograms of solvent. In your head, we're trying to solve for moles of solvent, so we can just multiply out kilograms of solvent. I wish I had that formula available for you, but write it down. Molality is equal to moles of solute, kilograms of solvent, and see what that would look like. And we're going to do that here as well. So moles of unknown will be equal to our molality times, and in parentheses, because we have to do some unit conversions for our mass of cyclohexane here. Remember to use the mass measured for part 3, not for part 2, which is our cyclohexane in that part. So we're doing our cyclohexane mass divided by 1,000. And that's because we are converting from grams to kilograms, because that is what we need in our formula for molality. Look that up if you're not familiar with it. Okay, so now we have our moles of unknown. Great. And we can find our molar mass of our unknown, because if you remember, molar mass is the grams per mole of a substance. And we have both the grams of our substance and its moles. So our molar mass of our unknown will be equal to its grams divided by its moles. Perfect. Now we have a molar mass. Yeah, I'm going to pause for a second, check everything is good. Okay, great. So now we know the molar mass of our unknown, and we've also calculated our freezing temperature for cyclohexane on part 1. as well as our KF value for cyclohexane, which is very important because remember that can only be determined experimentally. So that's something very impressive that you guys did. Let's see. So now we need to calculate how much error we got, and that unfortunately, with chemistry, there might be always a little bit of error. So let's see how bad this data set did, or I did. Okay, so our error is going to be equal to the absolute value, so that we don't really care about in what order we're subtracting, and we're going to do our freezing point for our regular cyclohexane, which is 7, minus the actual freezing temperature of cyclohexane, which is 6.5. And this is in degrees Celsius. And we're going to do that divided by the theoretical value once again. And that is not bad. It's 7%, not a bad error. Because remember, if we want to go from percent to, or from decimal to percent, we just do this. Well, okay, I'll do it this way, because there's actually a formatting in Excel that just does it for you and has a nice percent symbol, so you can click on this space. And then up here, there's a little percent sign. Cool. And you can add or subtract decimals if you're worried about sig figs, but don't worry about it for this one. By doing this, you can just move the decimal left or right, and it will just change your number to add or subtract the appropriate amount of digits. So I'm just going to leave it like that, just because I like it. And then same thing with our KF. We can do our KF value here. Oh, wait, absolute value. Don't forget absolute value. And then we're going to do KF minus our actual KF divided by the actual. And that is about 1%. Oh, because our KF value is negative, we'll also want absolute value there too. Let's see, hold on 1 second. Okay, let's just try doing it as a percent. And I think that'll fix it. And it's fine. It's about a 10% error, so not bad. So yeah, don't worry about your error too much. Use your actual results. And this is how we do the calculations for this experiment. If you're in my sections, check for an announcement of everything that you need to turn in for this report along with the plots. And make sure, one thing I didn't do here, I didn't add titles, I didn't add axis titles, and I didn't really make it very neat. So clean yours up a bit before you submit it. Or I guess you could hand draw it as well, as long as you have everything written out as it is here as well. Up to you. You can copy and paste them into, or like print them out and paste them into your lab notebook. Just make sure they're not coming loose so that I don't have loose graphs floating around and you would lose points. So don't have loose graphs floating around. It's up to you though, and I hope this helps. And thank you for watching. And bye.